What if everything we think we know about life on Earth is about to change? Look up at the night sky. Those distant stars and swirling galaxies hold secrets that could reshape our future in ways we're only beginning to understand. Throughout history, discoveries from space have rewritten the rules of science, from Galileo's telescope revealing Jupiter's moons to the cosmic microwave background, whispering the story of the universe's birth. But right now, we're on the edge of something even bigger. Scientists are uncovering mysteries beyond our solar system that could alter medicine, energy, even the very fabric of human existence. This isn't just about distant planets or black holes. It's about breakthroughs that might soon touch your daily life. Imagine a world where aging is reversed by studying astronauts' cells in zero gravity, where clean energy flows from reactor designs inspired by the sun's fusion, or where new materials stronger than diamond are crafted from the remnants of supernova. These aren't scenes from science fiction. They're real possibilities emerging from 30 of the most astonishing space discoveries of our time. Some of these findings are so revolutionary, they could solve crises like climate change or disease within decades. Others hint at phenomena so strange they challenge everything we thought we knew about physics. And the most thrilling part, many of these discoveries are happening right now, hidden in data from telescopes, space probes, and labs around the world. This journey will take you from the icy oceans of distant moons to the heart of dying stars, unraveling how each discovery could rewrite life as we know it. You'll hear about planets where rain falls as molten glass, about cosmic rays that may hold the key to immortality, and about bizarre space-time distortions that could make interstellar travel a reality. But more than just a list of wonders, this is about the human story behind them. The scientists who risked careers for radical ideas, the serendipitous accidents that led to breakthroughs, and the collective curiosity that drives us to keep looking up. By the end, you won't just see space differently, you'll see our future differently. So let's begin with the first discovery, one that's already changing how we think about survival beyond Earth. The discovery of liquid water buried beneath Mars' polar ice caps didn't just make headlines, it shattered our assumptions about the red planet. For decades, Mars appeared as a barren desert, a frozen wasteland where even the hardiest microbes would struggle to survive. But then, radar data from the European Space Agency's Mars Express orbiter revealed something extraordinary: vast reservoirs of liquid water hidden under layers of ice near the South Pole. This wasn't just a trickle or a fleeting damp patch. These were lakes, some spanning 12 miles across, buried nearly a mile beneath the surface. Suddenly, the question shifted from if Mars could harbor life to where it might be hiding. Water is the universal solvent, the foundation of every known form of life. Its presence means Mars could still be active beneath that dusty exterior, with chemical reactions or even microbial communities thriving in those dark, briny depths. But the implications stretch far beyond biology. Picture a future where astronauts land near these hidden lakes, drilling through the ice to tap into a ready-made resource. Water can be split into oxygen for breathing and hydrogen for rocket fuel, essentially turning Mars into a cosmic gas station for deeper space exploration. And if we can access these reservoirs, the dream of colonization shifts from science fiction to a tangible goal. Then there's terraforming. While transforming Mars into an Earth-like world sounds like a fantasy, liquid water is the first domino in a long chain of possibilities. Imagine redirecting comets to thicken the atmosphere or using algae to slowly seed the soil. Mars might never have oceans again, but these underground lakes could become the lifeblood of human outposts, sustaining greenhouses and shielding settlers from radiation. Of course, there are hurdles. The water is likely saltier than Earth's Dead Sea, and drilling through ice at -60 degrees Fahrenheit won't be easy. But here's what's electrifying. We've already found the starting point. Every great journey begins with a single step, and on Mars, that step just landed in a puddle. While Mars teases us with hints of hidden water, the real game changer might lie far beyond our solar system in the dim orbit of distant stars. Over the past decade, telescopes like Kepler and TESS have uncovered thousands of exoplanets, but a handful stand out, those nestled in the Goldilocks zone, where temperatures might allow liquid water and maybe life to exist. Take Proxima Centauri b, a rocky world just 4.2 light-years away, circling the closest star to our Sun. It's bathed in a perpetual crimson glow, tidally locked with one side eternally facing its faint red sun. Yet, in the twilight border between its scorching day and frozen night, there could be pockets where conditions are just right. Then there's the TRAPPIST-1 system, home to not one but 7 Earth-sized planets, 3 of which TRAPPIST-1e, F, and G sit snugly in that habitable sweet spot. Picture this, a star so small and cool that all 7 worlds orbit closer than Mercury does to our Sun, yet they might still harbor oceans. TRAPPIST-1e in particular has scientists buzzing. Computer models suggest it could be a water world with global seas deeper than Earth's, wrapped in a thick, nurturing atmosphere. The implications are staggering. If life can thrive there, it would prove that the universe is practically drenched in potential habitats. But here's where it gets even wilder. These discoveries aren't just about cataloging real estate for future vacations. They're rewriting the rules of planetary science. Proxima b's extreme radiation environment forces us to rethink how life might shield itself, perhaps in subsurface oceans or beneath layers of protective minerals. TRAPPIST-1 tightly packed planets could share atmospheres through comet impacts, trading organic molecules like cosmic pen pals. And then there's the ultimate dream. If we detect biosignatures, gases like oxygen or methane in their atmospheres, it would be the closest we've ever come to answering the age-old question, are we alone? Of course, getting there won't be easy. Proxima b's star unleashes violent flares that could strip away atmospheres, while TRAPPIST-1 worlds might be tidally squeezed into constant geologic upheaval. But that's the thrill of it. Each challenge forces innovation, like solar sails for faster travel or AI-driven probes that could outlive human lifespans to send back data. Imagine a future where we're not just staring at dots of light through telescopes, but analyzing weather patterns on alien worlds or even detecting city lights from civilizations we've yet to meet. The hunt for habitable exoplanets isn't just science, it's humanity's ultimate contingency plan, a reminder that among the stars there might always be another home waiting. Deep beneath the icy crust of Enceladus, Saturn's gleaming 6th largest moon, something extraordinary is erupting into space. When NASA Cassini spacecraft first observed towering geysers shooting from fractures near the moon's south pole, scientists were stunned, not just by the spectacle but by what those plumes contained. Hidden in the spray were complex organic molecules, the chemical building blocks essential for life as we know it. This wasn't just water vapor or simple gases. These were carbon-rich compounds, some with molecular weights over 200, far heavier than methane or ethanol. Suddenly, a moon barely 300 miles wide became one of the most promising places to search for life beyond Earth. The implications are staggering. Enceladus's subsurface ocean, kept liquid by the gravitational tug of war between Saturn and neighboring moons, isn't just a silent, dark abyss. It's an active chemical factory where hydrothermal vents might be churning out the ingredients for life. Picture Earth's deep sea vents where entire ecosystems thrive in total darkness, powered not by sunlight but by geothermal energy. Now imagine similar conditions but under miles of ice in an ocean that could span the entire moon. The discovery of organic molecules like benzene and formaldehyde suggests that Enceladus isn't just a passive ice ball. It's a dynamic world where carbon, hydrogen, and nitrogen could be mingling in ways that mimic Earth's primordial soup. What makes this even more tantalizing is the sheer accessibility of these materials. Unlike Mars, where we'd need to drill deep or scour ancient riverbeds, Enceladus is literally spewing its secrets into space. Future missions could fly through the plumes, sampling the ocean without ever landing. Imagine a probe equipped with advanced mass spectrometers, analyzing these molecules in real time, hunting for amino acids or even lipids, the telltale signatures of biology. If life exists there, it might be microbial, clinging to hydrothermal vents in a pitch-black ocean. But even that would rewrite the rules of astrobiology, proving that life doesn't need sunlight or a thick atmosphere. All it might need is liquid water, energy, and the right chemistry. Of course, Enceladus throws curveballs too. Its ocean is likely highly alkaline, with pH levels off the charts, and the pressure at those depths would crush most submarines. Yet extremophiles on Earth thrive in equally hostile places, from volcanic springs to nuclear reactor coolant pools. The bigger question isn't could life exist there, it's does it. Answering that could take decades, but the hunt itself is already reshaping science. Missions like the proposed Enceladus Life Finder aim to target specific biomarkers, while lab experiments on Earth simulate the Moon's peculiar conditions. Every step brings us closer to understanding whether we're alone or if the cosmos is far more alive than we ever imagined. Enceladus teaches us something profound. Life might not need a planet like ours at all. A tiny, ice-shrouded moon, invisible to the naked eye from Earth, could hold the key to one of humanity's oldest questions. And if its plumes truly contain the precursors of life, then the universe might be teeming with hidden oceans, each a potential cradle for something extraordinary. The search isn't just about finding microbes, it's about redefining what life is, where it can exist, and how common it might be among the stars. One of the most baffling signals from the cosmos arrives not as a whisper, but as a scream, a pulse of energy so intense it outshines entire galaxies for mere milliseconds. Fast radio bursts, or FRBs, are among the universe's greatest enigmas, packing the energy of 500 million suns into bursts shorter than the blink of an eye. First detected in 2007, these cosmic flares seemed like random anomalies until scientists noticed something chilling. A handful of them repeat. Imagine hearing a gunshot in a dark forest, only to realize the shooter is still out there, reloading. Theories about their origins range from the spectacular to the spine-tingling. Some bursts trace back to highly magnetized neutron stars, where stellar corpses called magnetars crack under pressure, unleashing tsunamis of radiation. Others might come from cataclysmic collisions, black holes swallowing neutron stars in a single gulp. But the most tantalizing possibility, these bursts could be artificial. Not natural disasters, but cosmic lighthouses, deliberate signals from civilizations advanced enough to harness unfathomable power. It sounds like science fiction, but consider this. In 2019, an FRB from a galaxy 1.5 billion light-years away repeated in a precise 157-day cycle like clockwork. Nature rarely keeps schedules that rigid. Decoding these bursts isn't just about solving a puzzle, it's about rewriting physics. Their journey across the cosmos leaves fingerprints, clues about the invisible matter between galaxies, the so-called missing baryons that form the universe's hidden scaffolding. Some bursts even arrive twisted, their waves polarized in ways that hint at extreme magnetic fields or warped spacetime. And if we could harness even a fraction of their energy, a single millisecond burst could power all of human civilization for centuries. Yet the real revolution might be in communication. If FRBs are natural, they're teaching us how matter behaves under conditions we can't replicate on Earth. But if they're artificial, they could be the first pages of an interstellar telegram. Projects like Breakthrough Listen now scan bursts for patterns that might encode information, searching essentially for a cosmic hello. Whether the answer lies in astrophysics or alien engineering, one thing's certain. Every time one of these bursts flashes across the void, the universe is trying to tell us something. The question is whether we're ready to listen. When Oumuamua streaked past the Sun in 2017, it wasn't just another space rock. It was a cosmic anomaly that defied every expectation. The first known visitor from another star system, this interstellar interloper didn't behave like any comet or asteroid we'd seen before. For starters, its shape was all wrong. Most asteroids are lumpy potatoes or rough spheres, but Oumuamua was flat, like a pancake tumbling through space, with some estimates suggesting it was 10 times longer than it was wide. Then there was its bizarre acceleration. Instead of slowing predictably as it moved away from the Sun, it sped up as if pushed by an unseen force. Scientists rushed to explain the mystery. Some argued it was a comet venting hidden gas that acted like a natural thruster, except telescopes detected no tail, no dusty plume, nothing. Others proposed it might be a shard of a shattered planet, sheared off by a cataclysmic collision in a distant system. But the most provocative theory came from Harvard astrophysicist Avi Loeb, who dared to ask, what if it wasn't natural at all? Oumuamua's peculiar acceleration and reflectivity, he noted, matched what we'd expect from a solar sail, a thin, artificial structure designed to catch starlight for propulsion. The idea sparked controversy, but it also opened a tantalizing door. Could this have been a relic of alien engineering, a discarded probe or a derelict craft adrift between the stars? The implications are staggering. If Oumuamua was artificial, even partially, it would mean we're not just searching for microbial life, but for civilizations capable of interstellar travel. And if it was natural, its oddities still rewrite the rules of planetary formation. Most solar systems eject debris during their chaotic early years, meaning space could be littered with such objects, some potentially rich in rare metals or even organic compounds. Imagine future missions intercepting these cosmic drifters, mining them for resources or decoding their origins like interstellar archaeologists. Yet the real lesson of Oumuamua is how little we truly know. It passed by too quickly for detailed study, leaving us with more questions than answers. Future telescopes, like the Vera Rubin Observatory, will scan the skies for more of these visitors, ready to capture their secrets before they vanish into the dark. Whether natural or not, Oumuamua was a wake-up call. The universe is far stranger than we imagined, and the next odd object hurtling into our solar system might not just be a curiosity, it could be a message. For centuries, black holes existed only in equations, mathematical ghosts lurking at the edge of understanding. Then, in April 2019, humanity stared directly into the abyss for the first time. The Event Horizon Telescope collaboration unveiled an image that made history. A fiery ring of light encircling the Inkai void of Messier 87's supermassive black hole 55 million light-years away. This wasn't just a snapshot, it was a triumph of human ingenuity, stitching together data from 8 radio telescopes across 4 continents to create an Earth-sized virtual lens capable of spotting a donut on the Moon. The image confirmed Einstein's century-old predictions with stunning precision. That glowing ring, its light bent by the black hole's gravity so severely that it wraps around space-time like water circling a drain. The dark shadow at its center, the event horizon, the point of no return where even light surrenders to the void. What's astonishing isn't just that Einstein was right, but how right. General relativity passed this cosmic stress test flawlessly, even under gravity 1 trillion times stronger than Earth's. Yet the implications stretch far beyond validation. That blurry orange ring is a gateway to new physics, offering clues about how space-time twists under extreme conditions, knowledge that could one day unlock gravity manipulation or even warp drive concepts. Here's where it gets even wilder. The tech behind this image is revolutionizing astronomy. The same interferometry techniques used to spot M87's shadow are now being adapted to study gravitational waves in unprecedented detail, potentially revealing hidden dimensions or quantum gravity effects. Some theorists suggest we might eventually manipulate gravitational lensing to create telescopes powerful enough to see the surfaces of exoplanets. Others envision using black holes as natural particle accelerators, probing energies far beyond anything achievable on Earth. But the real game changer lies in the unanswered questions. Why does the black hole's ring glow brighter on one side? Could that asymmetry hint at magnetic fields powerful enough to tear atoms apart, or even harnessable energy sources? And what happens to information swallowed by the singularity? Solving these riddles might require rewriting quantum mechanics itself. Projects like the Next-Gen Event Horizon Telescope aim to capture videos of black holes in action, watching as they devour stars or collide with neutron stars. Each frame could rewrite textbooks. This isn't just about understanding monsters lurking in galactic cores. It's about decoding the universe's deepest operating system. From the quantum foam of spacetime to the fate of information itself, black holes are cosmic Rosetta Stones, and we've just begun to translate them. Who knows? The key to interstellar travel or unified physics might be hiding in the next image pixels, waiting for us to look closer. While black holes and interstellar objects capture our imagination, there's an even greater mystery shaping the cosmos, one we can't see at all. Dark matter, that elusive substance making up 27% of the universe, has long been the ghost in the machine, silently sculpting galaxies and bending light with its gravitational pull. But now, for the first time, scientists are mapping its hidden tendrils in stunning detail, revealing a cosmic skeleton far grander than anything visible to our telescopes. These maps aren't just pretty pictures. Using techniques like gravitational lensing, where dark matter's gravity distorts the light from distant galaxies, researchers have reconstructed its invisible web across billions of light years. The results are humbling. Galaxies we see are mere ornaments dangling from this vast, dark architecture, with filaments so massive they could swallow thousands of Milky Ways. What's startling is how wrong our old models were. Dark matter isn't spread smoothly like butter. It clumps in ways that suggest unknown forces or even exotic particles beyond current physics. Now imagine harnessing this shadowy substance. If dark matter interacts with itself, as some theories suggest, future civilizations might tap into it as the ultimate energy source, a reservoir of mass energy dwarfing all the stars and planets combined. More radically, if certain hypothetical particles like actions exist, they could be manipulated to create propulsion systems unlike anything we've dreamed. Picture spacecraft surfing dark matter currents, using its gravitational tides as shortcuts through spacetime. It sounds fantastical, but remember, nuclear power once seemed impossible too. Yet the real breakthrough lies in what these maps reveal about our origins. The dark matter web structure hints at the universe's infancy, how tiny quantum fluctuations ballooned into the galactic superhighways we see today. Some filaments appear missing, suggesting dark matter might decay or transform over eons. Others align strangely, as if responding to forces from other dimensions. Each anomaly is a clue not just about the universe's hidden machinery, but about where it's headed. Will dark matter's grip eventually tear galaxies apart? Or could it be the scaffolding for civilizations to expand across voids we once thought impassable? The more we map, the clearer it becomes. Dark matter isn't just out there. It's the universe's hidden choreographer, and we're only beginning to learn its steps. Every new survey peels back another layer, bringing us closer to answers that could redefine energy, gravity, and our place in the dark. In August 2017, a ripple in spacetime sent scientists scrambling to telescopes around the world. For the first time, gravitational wave detectors caught the violent dance of two neutron stars colliding, a cataclysm so powerful it shook the fabric of the universe. This wasn't just another cosmic collision. It was a golden alchemy lab operating at temperatures of 1 trillion degrees, forging elements heavier than iron in its wake. The event, catalogued as GW170817, unfolded in a galaxy 130 million light-years away. As the neutron stars spiraled inward, they stretched and compressed spacetime itself, emitting gravitational waves detectable by LIGO and Virgo observatories. Just 1.7 seconds later, NASA's Fermi satellite picked up a gamma-ray burst, a deadly beacon of the merger's final moments. But the real show started when astronomers turned optical telescopes toward the spot. What they witnessed was a kilonova, an explosion 1,000 times brighter than a typical nova, glowing with the unmistakable signature of freshly minted heavy metals. Here's why this matters. For decades, we knew elements like gold, platinum, and uranium had to form somewhere beyond ordinary supernova. Now we had proof. Neutron star collisions are cosmic forges, where the extreme density smashes atoms together so violently that they capture neutrons in rapid succession, creating these precious elements through what's called the rapid neutron capture process. The numbers are staggering. That single event likely produced an amount of gold exceeding 10 times Earth's mass, scattered across space in a glittering cloud. The economic implications are mind-bending. If just one collision can seed a galaxy with precious metals, imagine the reserves drifting between stars enough to make every human a billionaire 1,000 times over. Futurists already dream of asteroid miners targeting these ancient kilonova remnants, though the technical hurdles are immense. More immediately, the discovery rewrote chemistry textbooks. We now know that the platinum in your catalytic converter, the gold in your jewelry, even the iodine in your thyroid, all originated in explosions like this, billions of years before our solar system existed. But the scientific payoff goes deeper. By comparing the gravitational wave signal with the light emitted, researchers tested Einstein's relativity with unprecedented precision, and it held up. The event even offered clues to the Hubble constant, measuring how fast the universe expands. Future detections might resolve lingering mysteries, like whether neutron star mergers birth magnetars or intermediate black holes. Some theorists speculate these collisions could produce strange quark matter, a hypothetical state denser than neutronium itself. What's exhilarating is how young this field is. With upgraded detectors coming online, we could spot neutron star mergers weekly, each a chance to study extreme physics we can't replicate on Earth. Imagine watching live as a kilonova unfolds, its spectrum revealing never-before-seen elements or exotic nuclear reactions. This isn't just astronomy. It's interstellar chemistry class, economics seminar, and physics lab rolled into one, all thanks to two dead stars that collided when dinosaurs still roamed Earth, finally sending their light and ripples our way. On the night of August 15, 1977, a volunteer astronomer named Jerry Amon sat scanning printouts from Ohio State's Big Ear radio telescope when his red pen stopped him cold. Circled on the page, surrounded by a sea of alphanumeric static, was a sequence so startling he scribbled, "Wow," beside it a name that would echo through history. The signal, 72 seconds of intense narrowband radio waves from the constellation Sagittarius, hit a frequency no natural cosmic process should produce. It was the holy grail SETI researchers had dreamed of, a transmission that looked, by every measure, artificially crafted. Then, just as suddenly as it appeared, it vanished, never detected again despite decades of searching. What makes the WOW signal so tantalizing isn't just its mystery, but its specificity. It blazed at 1420 MHz, a frequency shielded by international agreement from earthly transmissions, right where hydrogen, the universe's most common element, absorbs and emits energy. If you wanted to shout, "We're here," across the cosmos, this would be the cosmic equivalent of a flare gun in the dark. The signal's intensity spiked and faded exactly as expected for a distant source passing through the telescope's fixed beam, ruling out satellites or aircraft. Even today, after exhaustive attempts to pin it on comets, interstellar plasma, or equipment glitches, no natural explanation fully fits. Now imagine if we confirmed it was artificial. Not a cosmic hiccup, but a deliberate broadcast. That 72-second blip would become the most consequential message in human history, a proof we're not alone in a universe suddenly feeling far smaller. The philosophical shockwaves would dwarf Copernicus displacing Earth from the center of the solar system, or Darwin unraveling human origins. Religions, governments, and entire worldviews would recalibrate overnight. But the practical implications even wilder. If the signal came from a civilization capable of interstellar communication, their technology might be thousands or millions of years ahead of ours. That knowledge alone could leapfrog human progress, offering solutions to energy crises, disease, or even mortality. SETI efforts today are light years beyond 1977's tech. Projects like Breakthrough deploy AI to scan millions of frequencies simultaneously, while optical SETI hunts for laser pulses. Yet the WOW signal remains the gold standard, a reminder that first contact might not be a clear, repeated greeting, but a fleeting whisper we almost missed. Some theorists suggest it could have been a one-time beacon, a cosmic hello from a civilization that's since gone silent. Others propose it might have been a targeted message meant for someone else, brushing past us by accident. Here's the chilling thought: what if we're the ones who failed to reply? The signal's origin lies roughly in the direction of a sun-like star 200 light-years away. A response sent today wouldn't reach there until the year 2223, but perhaps that's the lesson. The WOW signal didn't just tease us with its ambiguity, it underscored how unprepared we are for the conversation to come. Every silent night since 1977, telescopes have listened for its return, knowing that one day the cosmos might not whisper but speak. And when it does, everything changes. Imagine a world where rivers carve valleys not with water, but with liquid methane, where rain falls in slow motion under an orange haze, and shorelines lap with hydrocarbons instead of saltwater. This isn't a dystopian sci-fi setting, it's Titan, Saturn's largest moon, and the only place in the solar system besides Earth with stable liquid on its surface. But here's what makes Titan truly revolutionary. Its methane cycle mirrors Earth's water cycle with eerie precision, offering scientists a natural lab to study chemistry that could rewrite energy production or even the origins of life. NASA Cassini mission peeled back Titan's thick nitrogen atmosphere to reveal a landscape straight out of a surrealist painting. Vast lakes near the poles, some larger than North America's Great Lakes, brim with liquid methane and ethane. Dunes made of organic sand, think frozen gasoline, stretch for miles, while cryovolcanoes might spew slushy mixtures of water and ammonia. But the real magic happens in the atmosphere. Sunlight breaks apart methane, triggering reactions that create complex organic molecules like ethylene and propane. These compounds rain down, pooling in lakes that slowly evaporate, completing a hydrocarbon cycle that's both alien and strangely familiar. Why should we care about a moon where the temperature hovers at -290 degrees Fahrenheit? Because Titan's chemistry could hold the key to cleaner fuels back on Earth. Methane is already a major energy source, but Titan's natural processes show how it forms, interacts, and transforms over time, insights that could lead to more efficient extraction or even synthetic alternatives. Some researchers speculate that microbial life might exist in Titan's methane lakes, using acetylene instead of oxygen for respiration. If true, it would prove life can thrive without water, dramatically expanding the cosmic real estate we consider habitable. Then there's the probiotic puzzle. Titan's thick organic haze resembles the primordial soup hypothesized to have spawned life on Earth. The moon's methane rivers might be mixing compounds that, given enough time, could self-assemble into something more complex. Future missions like Dragonfly, a nuclear-powered drone set to launch in 2027, will skim Titan's dunes and sample its atmosphere, hunting for molecular building blocks. Every finding could inch us closer to answering whether life is a cosmic fluke or an inevitability waiting for the right conditions, the most startling revelation. Titan teaches us that Earth's version of normal is just one possibility in a universe brimming with alternatives. A moon where the seas are flammable and the air smells like a petroleum refinery might be the very place that unlocks sustainable energy or rewrites the definition of life itself. As we peer through Titan's haze, we're not just exploring another world, we're glimpsing the infinite flexibility of nature and perhaps our own future. The universe should be teeming with life. With billions of habitable planets in our galaxy alone, why haven't we found a single whisper of another civilization? This eerie silence is the heart of the Fermi paradox, and the answers we're uncovering now could determine whether humanity survives the next 1,000 years or vanishes without a trace. One explanation sends chills down the spines of astrobiologists, the Great Filter. This theory suggests that at some point between a planet's birth and the rise of a spacefaring civilization, there's an almost insurmountable barrier, a cosmic bottleneck that snuffs out intelligent life before it can spread. The terrifying question isn't just where this filter lies, but whether we've already passed it or if it's still ahead of us. If it's behind us, say, the improbable leap from single-celled to multicellular life, then we might be rare miracles in a quiet universe. But if it's ahead, nuclear war, runaway AI, climate collapse, then every advanced civilization might be doomed to self-destruct just as they reach the brink of interstellar communication. Recent discoveries add grim weight to this idea. Astrophysicists studying dead zones around young stars found that violent solar flares could strip atmospheres from otherwise habitable planets, leaving them barren. Meanwhile, models of technological civilizations suggest most might overconsume resources and collapse within centuries. The haunting lesson: the universe might be littered with the ruins of civilizations that never made it. Yet there's hope in the paradox. If the filter is behind us, we're custodians of a precious spark, tasked with ensuring it doesn't flicker out. If it's ahead, recognizing it gives us a fighting chance to navigate around it. That's why initiatives like nuclear disarmament and AI ethics aren't just political debates, they're survival strategies written in the ashes of hypothetical alien civilizations. The silence of the cosmos might be the most important warning we'll ever receive. Heeding it could mean the difference between becoming interstellar explorers or just another layer in some future alien paleontologist's fossil record. Picture two particles separated by thousands of miles, yet changing their properties in perfect sync. No wires, no signals, just instant connection, as if space meant nothing at all. This isn't telepathy or science fiction, it's quantum entanglement, one of the universe's most baffling phenomena. And recent experiments aboard the International Space Station have proven this spooky link doesn't just work across labs, it thrives across continents, even Earth and orbit. In 2017, China's Misha satellite shattered records by beaming entangled photons to ground stations 747 miles apart while they remained perfectly correlated. The result: quantum communication doesn't just survive the harsh radiation and vacuum of space, it thrives there. Here's why this rewrites the rules of technology. Entangled particles could form the backbone of unhackable quantum networks. Traditional encryption relies on math problems so complex they'd take centuries to crack, but quantum computers could smash them in minutes. Quantum key distribution, however, uses entanglement to create codes that collapse the instant an eavesdropper tries to intercept them. China already demonstrated this by hosting the first quantum-secured video call between Beijing and Vienna, shielded by photons that self-destruct if tampered with. Imagine banks, governments, or military systems protected by physics itself, where any breach attempt triggers an automatic shutdown. But the truly revolutionary potential lies in defying Einstein's ultimate speed limit. When entangled particles sink instantaneously across vast distances, they're not sending information faster than light, at least not in the traditional sense. Yet this loophole could enable quantum teleportation, where data jumps between particles without traveling the space between them. Researchers at Caltech successfully teleported quantum states over 27 miles using fiber optics, and space-based tests aim for intercontinental leaps next. The implications: a future quantum internet where transactions, communications, and AI computations happen at speeds that make today's lag seem prehistoric. Of course, the universe doesn't give up its secrets easily. Maintaining entanglement over long distances requires ultra-cold temperatures and shielding from cosmic interference. Mishus's success rate was just 1 photon pair per 6 million attempts, hardly practical for mass use. Yet labs worldwide are racing to boost efficiency, with some experimenting with quantum repeaters that extend entanglement like cosmic relay stations. Private ventures even plan constellations of quantum satellites, weaving a global web of unhackable connectivity. The wildest twist: entanglement might not be limited to tiny particles. Some theorists suggest macroscopic objects, even humans, could one day entangle with quantum duplicates in orbit, enabling instantaneous data transfer between bodies separated by space. It sounds outrageous, but remember, so did wireless communication a century ago. Every experiment peeling back another layer of quantum weirdness brings us closer to technologies that'll make today's internet look like smoke signals. The universe, it seems, has been running a quantum network all along. We're just now learning to tap into it. At the frozen edge of our solar system, far beyond Neptune's orbit, lies a graveyard of cosmic relics so pristine, they're practically time capsules from the birth of the planets. The Kuiper Belt, a vast ring of icy bodies, holds objects like Arakoth, a bizarre snowman-shaped world that's barely changed in 4.5 billion years. When NASA New Horizons spacecraft zipped past it in 2019, scientists didn't just see a curious shape. They glimpsed the raw building blocks of Earth itself, frozen in deep space like ingredients left on a forgotten shelf. Arakoth's twin lobes, gently pressed together in what researchers call a contact binary, tell a story of cosmic patience. Unlike planets forged by violent collisions, this 22-mile-wide object formed from a slow, delicate dance between two separate bodies that barely touched as they merged. Its smooth surface, unmarked by craters or erosion, suggests it's one of the most primordial objects ever studied, a fossil from the era when dust specks first began clumping into worlds. But the real treasure lies in its composition. Spectroscopy revealed organic molecules like methanol ice and complex tholins, the same carbon-rich compounds that might have seeded life on Earth. What makes the Kuiper Belt's inhabitants so revolutionary isn't just their age, but their isolation. While asteroids in the inner solar system were baked by sunlight and pummeled by impacts, Kuiper Belt objects like Arakoth remained in a deep freeze, preserving chemistry from the solar system's infancy. Some even contain nitrogen ice so untouched, it still carries isotopic signatures of the interstellar cloud that birthed our sun. These aren't just rocks, they're recipes, showing how simple ices and organics could have hitchhiked to Earth via comets, delivering the ingredients for oceans and probiotic chemistry. Yet the surprises don't stop there. Other Kuiper Belt oddities, like the ultra-red dwarf planet Sedna or the wildly tilted orbit of Haumea, hint at a turbulent youth for our solar system. Some may be kidnapped objects from another star's influence during the sun's early days in a dense stellar nursery. Others, like the possible existence of a massive Planet 9 lurking even farther out, suggest our cosmic neighborhood is far from settled. Every new discovery peels back another layer, revealing a solar system that's less a orderly clockwork and more a mosaic of stolen worlds, survivors, and celestial drifters. The true value of these icy sentinels isn't just academic. Understanding how their organic molecules assembled or failed to could guide synthetic biology on Earth, helping us engineer life from scratch. And if humanity ever ventures beyond Mars, the Kuiper Belt's reservoirs of water, ice, and methane could become interstellar pit stops, fueling ships bound for the stars. Right now, missions like Japan's planned Okonos aim to land on a Kuiper Belt object, drilling into its surface to taste chemistry older than the continents. As strange as these frozen worlds appear, they might hold the most familiar story of all: how a cloud of dust and gas became a place where life could blossom. The Kuiper Belt isn't just the solar system's attic. It's the closest thing we have to a family album, with each page written in ice and stardust. The sun might seem eternal and unchanging from our vantage point on Earth, but its surface tells a different story, a roiling, violent dance of magnetic storms capable of unleashing chaos across the solar system. In 2012, a solar flare narrowly missed Earth, a coronal mass ejection so powerful it could have fried satellites, collapsed power grids, and plunged continents into darkness for months. Scientists later calculated it was one of the strongest storms ever recorded, comparable to the Carrington event of 1859, when auroras lit skies as far south as Cuba and telegraph operators received shocks just from touching their equipment. Today, with our planet more interconnected than ever, a similar event could cause up to $2 trillion in damage globally. But here's the game-changing development: we're no longer blind to these threats. Breakthroughs in solar forecasting are giving us something humanity has never had before: a cosmic early warning system. At the heart of this revolution are missions like NASA's Solar Dynamics Observatory and the European Space Agency's Solar Orbiter, armed with instruments that peer into the sun's magnetic heart. By tracking the tangled webs of magnetic fields that spawn flares, researchers can now predict eruptions up to 48 hours in advance with 80% accuracy. Machine learning has turbocharged these efforts, analyzing decades of solar data to spot subtle patterns preceding storms, like how earthquake forecasters watch for seismic tremors. One algorithm even identified a telltale, sigmoid shape in magnetic fields that signals an imminent X-class flare, the most powerful category. But forecasting is only half the battle. The real triumph lies in mitigation. Utilities worldwide are installing grid armor, transformers that automatically disconnect during surges, mimicking how surge protectors shield your home electronics. After Sweden upgraded its grid following a near-miss solar storm in 2015, simulations showed it could withstand a Carrington-level event with minimal disruptions. Meanwhile, satellite operators are developing rapid shutdown protocols, shielding sensitive electronics or orienting spacecraft to present their most armored faces to incoming radiation. Even undersea internet cables vulnerable to solar-induced currents are being retrofitted with fiber optic repeaters less susceptible to electromagnetic interference. The stakes stretch beyond infrastructure. Solar storms pump radiation into Earth's atmosphere, posing risks to astronauts and high-altitude flights. During a 2021 flare, airline crews on polar routes absorbed the equivalent of a chest X-rays worth of radiation in just hours. New models now predict these radiation bursts down to the minute, allowing airlines to reroute flights and the International Space Station to retreat to more shielded modules. There's even a push to extend solar weather alerts to public emergency systems, treating flares like hurricanes or tornadoes, threats you might one day see scrolling across your phone with instructions to unplug devices or avoid non-essential travel. Perhaps the most radical idea: fighting fire with fire. Experimental projects aim to deflect incoming storms using magnetic parasails deployed from satellites, or by firing high-energy plasma beams to disrupt a flare's trajectory. It sounds like science fiction, but in 2023, a team at the University of Michigan successfully steered a simulated coronal mass ejection in a lab using precisely timed electromagnetic pulses. Scaling this up could take decades, but the principle is sound. If we can't stop solar flares, maybe we can nudge them harmlessly off course. What makes this era extraordinary isn't just the technology, it's the shift in mindset. For most of history, humanity cowered under the sun's whims. Now, we're learning to read its moods and brace for its outbursts. Every advance pulls us further from the dark ages, literally. Because in a world powered by silicon and satellites, a single unshielded solar storm could send us tumbling back centuries. But for the first time, we're not just potential victims. We're forecasters, we're engineers, we're a civilization learning to look its star in the eye and stand its ground. Somewhere in the vast cosmic darkness, beyond the reach of our most powerful telescopes, an invisible force tugs at everything around us, a gravitational pull so immense it's dragging entire galaxies toward it at breakneck speeds. Astronomers call it the Great Attractor, and it remains one of the most puzzling enigmas in modern cosmology. Picture throwing a ball into the air, only to watch it curve sideways instead of falling back down. That's essentially what's happening to our Milky Way, along with thousands of other galaxies, as they're yanked toward this mysterious region of space over 650 million light-years away. What makes this anomaly so baffling isn't just its strength, but what lies behind it. Initial observations in the 1970s and 80s suggested a concentration of mass equivalent to tens of thousands of Milky Ways. Yet when astronomers pointed optical telescopes in that direction, they found almost nothing. The Great Attractor sits obscured by our own galaxy's dusty disk, a cosmic blind spot dubbed the Zone of Avoidance. X-ray and radio telescopes later pierced through this veil, revealing a sprawling supercluster of galaxies dubbed the Norma Cluster at the heart of the attraction. But here's the twist: even this colossal structure isn't nearly massive enough to explain the gravitational pull we're witnessing. There's something else lurking there, something unseen. Theories about what's really behind this cosmic tug-of-war range from the revelatory to the mind-bending. Some astrophysicists propose an unfathomably dense knot of dark matter, a gravitational anchor woven from the universe's invisible scaffolding. Others speculate it might be the foothold of something even larger, a supermassive structure like the Shapley Attractor, an even more distant concentration of galaxies pulling the Great Attractor itself. Then there are the radical ideas. Could this be evidence of higher dimensions warping space-time in ways we can't yet measure, or even a gravitational echo from a neighboring universe brushing against our own in the cosmic bulk? Unraveling this mystery could rewrite physics as we know it. If the Great Attractor's pull stems from exotic matter or hidden dimensions, tapping into those forces might unlock energy sources beyond our wildest dreams. Imagine manipulating gravity itself to power interstellar travel or harness zero-point energy. Even the dark matter hypothesis could revolutionize technology. Learning to detect and interact with these invisible particles might allow us to build materials with programmable gravity or shields against cosmic radiation. But the biggest revelation might be philosophical. The Great Attractor forces us to confront how little we truly see of the universe. 95% of reality is composed of dark matter and dark energy, invisible to our instruments. Every time we think we've mapped the cosmos, anomalies like this remind us we're still children tracing shapes in the cosmic sand, unaware of the tide just beyond our sight. Future telescopes like the Square Kilometre Array aim to map this hidden gravitational landscape in unprecedented detail. What they find could either solve the puzzle or plunge us deeper into the mystery. One thing's certain: the universe still holds forces that don't just move galaxies, but reshape our understanding of existence itself. Bacteria clinging to a meteorite frozen in the void between stars might sound like the opening scene of a sci-fi thriller, but it's a hypothesis with mounting evidence. Meet panspermia, the radical idea that life doesn't just originate on planets, but hitchhikes across the cosmos on comets, asteroids, and cosmic dust. Recent experiments on the International Space Station have turned this theory from fringe speculation into a serious scientific pursuit. When researchers exposed hardy microorganisms like Deinococcus radiodurans, nicknamed Conan the bacterium, to the vacuum, radiation, and extreme temperatures of space for years, these extremophiles didn't just survive. They thrived, reactivating once brought back to Earth-like conditions. If microbes can endure interstellar journeys shielded inside rocks, the implications are staggering. Life might not be unique to Earth at all, but a cosmic traveler with countless potential homes. The smoking gun for panspermia might already be in our hands, or more accurately, in our meteorite collections. The Murchison meteorite, which crashed in Australia in 1969, contained over 70 different amino acids, including some not found on Earth. These building blocks of life didn't just survive atmospheric entry, they formed in space, proving complex organic chemistry operates far beyond our planet. Even more compelling, in 2020, Japanese scientists found intact protein-like structures inside the Ekfur 086 meteorite molecular machines that could kickstart life's earliest reactions. While this doesn't confirm extraterrestrial biology yet, it shows the universe is prepping the ingredients for life everywhere like a cosmic sous chef. But the real game changer lies in biotech and space exploration. If microbes can hop between worlds, contamination isn't just a risk, it's a certainty. NASA planetary protection protocols, once focused on keeping Earth sterile to avoid false positives in alien life detection, now grapple with a new reality. We might be spreading Earth's microbes to Mars via rovers or vice versa. Some astrobiologists argue we should embrace this, seeding barren worlds with extremophiles to terraform them. Imagine algae engineered to survive Martian soil, exhaling oxygen for future colonists, a literal breath of life carried on human spacecraft. The darker twist, panspermia could explain why life appeared on Earth so fast. Fossil evidence suggests microbes existed just a few 100 million years after the planet cooled, geologically instantaneous. If life didn't start here but arrived here, it solves the puzzle of how complex chemistry bootstrapped itself so quickly. The universe might be teeming with life, not because it arises easily, but because it spreads relentlessly like dandelion seeds on a galactic wind. Future missions could settle the debate. Europa Clipper, launching to Jupiter's icy moon in 2024, will analyze plumes for Earth-like DNA. Mars sample return missions might uncover microbes fossilized in ancient lake beds, or worse, living ones we brought there decades ago. Either result reshapes humanity's place in the cosmos. We're either the lone sparks in a sterile universe or just the newest tenants in an ancient, interconnected web of life that's been swapping genetic material across the stars for billions of years. Panspermia doesn't just challenge where life began, it redefines what it means to be from somewhere. Your DNA, your cells, the very water in your body, all might carry stardust, not just metaphorically but literally, forged in distant nebulae and delivered by comets. We're not just Earthlings, we're citizens of the galaxy. Beneath Europa's cracked, icy shell lies an ocean so vast, it could hold twice the water of all Earth's seas combined, and it's not just sitting still. This frozen moon of Jupiter churns with tidal forces so powerful, they keep its hidden waters liquid despite the bitter cold of space. When NASA Galileo spacecraft first detected Europa's magnetic field fluctuations in the 1990s, scientists knew they'd found something extraordinary. The data pointed to a global, salty ocean, sloshing beneath an ice crust up to 15 miles thick. But the real shock came when Hubble spotted plumes of water vapor erupting from Europa's surface in 2013. Geysers blasting material into space, offering a potential shortcut to sample this alien sea without drilling through miles of ice. What makes Europa's ocean so tantalizing isn't just its existence, but its chemistry. Hydrated salts like magnesium sulfate coat the moon's fractures, suggesting the water interacts with a rocky seafloor, a recipe for hydrothermal vents. On Earth, such vents are teeming with life, from giant tube worms to heat-loving bacteria that thrive on sulfur and methane. If Europa's dark depths harbor similar extremophiles, they'd challenge every assumption about where life can exist. But the implications go far beyond biology. Enzymes from Earth's deep-sea microbes already revolutionize industries, from detergents that work in cold water to DNA polymerases used in PCR tests, including those for COVID. Imagine what compounds we might discover in Europa's even stranger environment, where organisms could have evolved to harness silicon instead of carbon, or thrive under pressures that would crush submarines. That's why NASA Europa Clipper mission, launching in 2024, isn't just another planetary probe. Packed with ice-penetrating radar and mass spectrometers, it'll skim Europa's surface at just 25 miles altitude, tasting those geyser plumes for amino acids, lipids, or even complex cells. One instrument, aptly named SURFAC, will analyze dust particles ejected by meteorite impacts, hunting for organic material. Meanwhile, the lander concept being developed for a follow-up mission could deploy a nuclear-powered tunnelbot to melt through the ice, potentially reaching the ocean within weeks. The engineering hurdles are immense. Europa's surface radiation is lethal, and its ice shell likely has jagged, shifting layers, but the payoff could redefine astrobiology. Beyond the search for life, Europa's ocean offers a masterclass in planetary survival. Its waters have persisted for billions of years despite the Moon's distance from the Sun, thanks to Jupiter's gravitational kneading. This tidal heating might be the key to future human outposts, where we could tap subsurface oceans on icy worlds for water, oxygen, and even energy. Some researchers speculate that Europa's chemistry could inspire new forms of renewable energy, perhaps microbial fuel cells that generate electricity in extreme cold, or enzymes that break down pollutants at sub-zero temperatures. Yet the most profound lesson Europa teaches is about resilience. In the darkness under that ice, cut off from sunlight and photosynthesis, life might have found another way, just as it did in Earth's deepest caves and hottest vents. If we find even single-celled organisms there, it would prove that life isn't a fluke confined to Goldilocks zones, but a cosmic imperative adapting to the harshest corners of existence. Europa's ocean isn't just a scientific target, it's a mirror showing us how little we know about the tenacity of life and how much we have yet to discover in our own backyard. For nearly a century, astronomers have relied on one constant to map the cosmos, the Hubble constant, a number representing how fast the universe expands. But here's the unsettling truth: depending on how you measure it, you get wildly different answers. This discrepancy, dubbed the Hubble tension, isn't just a minor math error. It's a cosmic crisis that might force us to rewrite the laws of physics. Take two of our most trusted measurement methods. The first studies the cosmic microwave background, the afterglow of the Big Bang, using data from Planck satellite observations. This approach suggests the universe expands at about 67 kilometers per second per megaparsec. The second method tracks pulsating stars called Cepheids and exploding supernova in nearby galaxies, pegging the rate at 73. That 6-kilometer gap might sound tiny, but statistically, it's like weighing yourself on two scales, one saying you're 100 pounds, the other insisting you're 200. The difference isn't just noise, it's a screaming anomaly. What makes this tension electrifying is what it implies about the universe's hidden machinery. One possibility: dark energy, the mysterious force accelerating cosmic expansion, isn't constant after all. Maybe it's growing stronger, warping space-time faster than our models predict. Alternatively, dark matter could interact with ordinary matter in ways we've never detected, subtly skewing measurements. The most radical theories propose entirely new particles or forces, like early dark energy, that briefly surged after the Big Bang, leaving fingerprints in the ancient light we observe today. The stakes couldn't be higher. If the Hubble tension holds, it could mean our entire cosmological framework, the Lambda CDM model, is incomplete. This model, which has guided astronomy for decades, assumes dark energy and dark matter behave in specific, stable ways. But the tension suggests the universe might be playing by different rules, with forces that evolve or interact unpredictably. Imagine discovering the rules of chess you've memorized suddenly changed mid-game. That's the scale of recalibration cosmologists now face. New telescopes are joining the hunt for answers. The James Webb Space Telescope is scrutinizing Cepheid stars with unprecedented precision, while next-generation observatories like the Vera Rubin Telescope will map billions of galaxies to cross-check expansion rates. Some experiments even probe the clumpiness of matter in the early universe, hunting for oddities that might explain the mismatch. Every dataset either deepens the mystery or inches us toward a breakthrough. Here's the thrilling part: resolving the Hubble tension could unlock technologies beyond our imagination. If dark energy fluctuates, could we one day harness it? If new particles exist, might they revolutionize energy or propulsion? Even if the answer is less dramatic, the pursuit reshapes our tools. Gravitational wave detectors, quantum sensors, and AI-driven simulations are all being refined to crack this puzzle. The Hubble tension isn't just a problem. It's a portal forcing us to question assumptions that have defined our cosmic worldview for generations. And whatever lies on the other side will change not just how we see the universe, but how we see our place within it. Most planets we know orbit stars, dutifully circling their suns like children around a campfire. But not all. Lurking in the interstellar dark are rogues, worlds untethered from any star, drifting alone through the cosmic void. These wandering planets aren't just curiosities. They're time capsules, way stations, and potential treasure troves that could rewrite the future of space exploration. The first confirmed rogue planet turned up in 2016, when astronomers spotted a Jupiter-sized object floating freely near a young star system. Since then, surveys like OGLE and microlensing projects have revealed thousands more, some as close as a few dozen light-years from Earth. These orphans likely formed two ways: either ejected from their birth systems by gravitational chaos, or born directly from collapsing gas clouds too small to ignite as stars. The sheer number is staggering. Estimates suggest there could be 20 times more rogue planets in our galaxy than stars, a silent majority hiding in plain sight. What makes these drifters revolutionary isn't just their abundance, but their potential utility. Picture a future where interstellar ships refuel not at stars but at rogue planets. Many likely harbor subsurface oceans kept liquid by geothermal heat or radioactive decay, vast reservoirs of water convertible into hydrogen fuel and oxygen. Others might be rich in rare metals like platinum or iridium, concentrated by ancient volcanic activity with no star to strip them away. Unlike asteroids, their gravity could anchor mining operations, eliminating the need for complex orbital stabilization. Some might even have thick atmospheres, offering natural radiation shielding for temporary bases. Cosmic pit stops on the highway between stars. Then there's the biological angle. Rogue planets near nebulae or with active cores could host hydrothermal vent-like ecosystems, thriving in perpetual darkness. Even barren ones might preserve prebiotic molecules in their ice, undisturbed for billions of years. Missions like NASA's upcoming Nancy Grace Roman Space Telescope will hunt for these worlds using microlensing, where a planet's gravity briefly magnifies the light of distant stars. Each discovery could reveal a new class of celestial body: super-Earths with diamond cores, frozen gas giants with metallic hydrogen layers, or even worlds with exotic matter states impossible under stellar heat. Perhaps the most tantalizing rogue planets are the Steppenwolf-type rocky worlds heated not by stars, but by internal nuclear reactions or tidal flexing. These could maintain habitable conditions under ice shells for eons, long after their suns died. If life exists there, it wouldn't need photosynthesis or even a traditional day-night cycle, just chemistry, energy, and time. Rogue planets force us to rethink what makes a world alive. They're proof that solar systems don't have a monopoly on planetary formation, and that the universe is far more creative with its real estate than we ever imagined. The next great leap in exploration might not be toward a star, but into the deep dark, where untethered worlds wait, holding secrets, resources, and perhaps even new chapters for life itself. 60 years ago, scientists could only guess what powered the solar wind, that million-mile-per-hour stream of charged particles blowing past Earth. Then NASA's Parker solar probe did the unthinkable. It dove closer to the sun than any spacecraft in history, enduring temperatures hot enough to melt steel to uncover secrets that could revolutionize energy and protect our technological civilization. What it found in the sun's corona, the wispy outer atmosphere visible during eclipses, defied every expectation. Instead of gradually cooling as it moves away from the sun's surface, the corona heats up to millions of degrees, a counterintuitive puzzle known as the coronal heating problem. Parker's instruments revealed violent magnetic explosions called nanoflares, each packing the power of a 10-megaton hydrogen bomb, constantly erupting across the sun's surface. These miniature detonations pump energy into the corona like a cosmic espresso machine, accelerating particles to unimaginable speeds. Even more startling, the probe caught the solar wind changing gears, transitioning from orderly magnetic waves near the sun to turbulent, high-speed streams farther out. This turbulence could explain how the wind gains enough energy to buffet planets light years away. These discoveries aren't just academic. Understanding the solar wind's mechanics could unlock breakthroughs in fusion energy. Tokamak reactors on Earth struggle to contain plasma as hot as the corona, but Parker's data reveals how the sun's magnetic fields naturally stabilize and accelerate charged particles. Scientists at MIT are already mimicking these processes, using advanced magnets to recreate coronal conditions in lab-scale reactors. If successful, we might crack the code to limitless clean energy by copying the sun's blueprint. Then there's space weather forecasting. Solar storms can cripple power grids and satellites, like the 2022 event that destroyed 40 SpaceX Starlink satellites. Parker identified switchbacks, sudden magnetic zigzags in the solar wind that precede major eruptions. Tracking these could give astronauts and grid operators days of warning instead of hours. Private companies like Space Weather Tech now incorporate Parker's models into real-time alert systems, helping airlines reroute flights and utilities shield transformers ahead of storms. The probe also stumbled upon a potential solar oddity: dust-free zones near the sun where intense heat vaporizes interstellar debris. This revelation could inspire next-gen heat shields for spacecraft, using similar physics to shed orbital debris or even deflect asteroid impacts. Parker's final dive in 2025 will skim just 4 million miles from the sun's surface, close enough to witness magnetic reconnection events as they happen. Each byte of data beamed back isn't just solving mysteries. It's handing us tools to harness the star that gives us life while preparing for its tantrums. The probe's legacy won't be written in scientific papers alone, but in blackout-proof cities, fusion-powered grids, and perhaps one day, engines that ride the solar wind itself. Picture the universe not as scattered islands of galaxies, but as a grand interconnected tapestry, a vast cosmic web where threads of dark matter stretch billions of light years, weaving galaxies together in delicate filaments. This isn't just artistic imagination. In 2014, astronomers using the Sloan Digital Sky Survey finally mapped a small section of this web in 3 dimensions, revealing a structure so colossal it makes superclusters look like specks. These filaments, often called the Universal Highway System, aren't empty. They're bustling with hot gas, rogue planets, and wandering stars, all funneled along gravity's hidden scaffolding. But what's truly mind-blowing isn't just the web's existence, it's how little we've seen of it. less than 10% has been charted, meaning we're like ants staring at a single thread of a sprawling spiderweb, oblivious to its full design. The cosmic web's filaments are more than just galactic connectors, they're time machines. Because light takes billions of years to cross them, studying their structure lets us peer into the universe's adolescence. Some filaments appear distorted, as if tugged by unseen forces, hinting at dark energy's fingerprints. Others glow faintly with the ultraviolet signatures of ionized hydrogen, leftover fuel from the Big Bang. The most ambitious mapping project yet, the Dark Energy Spectroscopic Instrument in Arizona, aims to catalog 35 million galaxies by 2026, reconstructing the web's growth over 11 billion years. The goal, to catch dark energy in the act, watching how its repulsive force alters the web's expansion over cosmic time. Hidden within these filaments could be universes within universes. Theorists propose that galaxy strings and dense knots where multiple filaments intersect might harbor thousands of orphaned stars too dim to spot from Earth. Some could even host rogue planets warmed by cosmic radiation, creating pocket habitats in the void. Even wilder, primordial black holes forged in the early universe's chaos might lurk along these threads like spiders waiting for prey, their gravity subtly bending the web's structure. Future telescopes like the European Space Agency's Euclid will hunt for these distortions, potentially uncovering black holes dating back to the first seconds after the Big Bang. But the web's practical applications might hit closer to home. Its filaments act as gravitational lenses, magnifying distant objects behind them. Astronomers are already exploiting this to spot galaxies otherwise too faint to see, but next-gen telescopes could turn the entire web into a cosmic microscope. Imagine resolving the surfaces of exoplanets light years away by using a filament's lensing effect like a giant magnifying glass. There's even speculation that advanced civilizations might harness these filaments as navigation beacons or energy highways, tapping into the dark matter currents flowing along them like cosmic power lines. The most humbling realization, we're not just observers of the cosmic web, we're part of it. The Milky Way sits on a filament's edge, slowly drifting toward the massive Shapley supercluster like a leaf caught in a gentle current. Every atom in your body once traveled these threads, assembled from stardust that moved along the same gravitational rivers we're now mapping. The cosmic web doesn't just connect galaxies. It connects us to each other, to the universe's past, and to futures we're only beginning to imagine. As we chart its invisible roads, we might not just solve dark energy's mystery. We might find our place in something far larger than we ever dreamed. On the rusty plains of Mars, a faint whiff of gas keeps rewriting the rules of planetary science: methane, a simple molecule with explosive implications. Since the Curiosity rover first detected mysterious methane spikes in 2013, each new reading has deepened the mystery. Unlike Earth, where methane overwhelmingly comes from living organisms, cow burps, rotting plants, or natural gas deposits, Mars shouldn't have active sources of this gas. Yet seasonal plumes keep appearing, sometimes vanishing within hours, as if the planet itself is exhaling secrets. The debate hinges on two possibilities, each tantalizing in its own way. On one side, geology. Mars could be venting methane trapped in ancient underground reservoirs, released by seismic activity or chemical reactions between water and olivine-rich rocks. The ESA's Trace Gas Orbiter found evidence of chlorine compounds that might accelerate methane destruction in the atmosphere, explaining its fleeting appearances. But here's the twist: Curiosity's measurements show methane rising at night near Gale Crater, suggesting an underground source actively replenishing it. If true, Mars isn't just a frozen relic, it's geologically alive with processes we've yet to understand. Then there's the electrifying alternative: biology. On Earth, certain microbes called methanogens thrive in oxygen-free environments like swamps or animal guts, belching methane as a byproduct. If similar organisms exist beneath Mars' permafrost, shielded from radiation and drawing energy from hydrogen or carbon dioxide, their metabolic fingerprints could explain the spikes. The Rosalind Franklin rover, set to launch in 2028, carries a drill capable of digging 6 feet down deep enough to potentially reach these hypothetical microbes. Even if the methane isn't biological, its presence hints at resources future colonists could exploit. Methane breaks down into hydrogen and carbon, key ingredients for fuel and life support systems. The implications stretch beyond Mars. If methane signals life here, icy moons like Enceladus or exoplanets with methane-rich atmospheres suddenly become prime hunting grounds. Conversely, if it's purely geological, we've uncovered a new planetary process that could reshape how we interpret atmospheric data across the cosmos. Every whiff of methane is a breadcrumb leading us closer to answering whether life is a cosmic fluke or an inevitability hiding in plain sight. The red planet isn't just a neighbor. It's a test case, forcing us to refine our tools and assumptions before we search farther afield. One day, these faint traces might mark the spot where humanity found its first extraterrestrial companions, or learn just how clever dead rocks can be. If black holes are the universe's ultimate one-way streets, white holes could be their cosmic exit ramps, theoretical portals where matter and energy erupt back into reality after vanishing into a black hole's depths. While no white hole has ever been observed, their potential existence emerges straight from Einstein's equations of general relativity, painting a universe where every black hole might conceal a fiery rebirth on the other side. Imagine a singularity in reverse, a point in space where nothing can enter, only explode outward at velocities approaching light speed, ejecting everything it once swallowed in a dazzling burst of radiation and particles. The energy release would dwarf supernova, lighting up galaxies like a cosmic flashbang, proving white holes could unravel some of physics' greatest mysteries. For decades, scientists have grappled with the information paradox, the idea that black holes seemingly erase all traces of what they consume, violating quantum mechanics' rule that information can't be destroyed. White holes offer an elegant solution. Perhaps the information isn't lost at all, but encoded in the radiation and matter they spew back out. If true, this would bridge the chasm between general relativity and quantum theory, forging a unified framework for how the universe operates at every scale. Some researchers even speculate that the Big Bang itself might have been a primordial white hole event, the ultimate cosmic reset button. Then there's the energy angle. A controlled white hole, if such a thing could ever be harnessed, would be the ultimate power source. Calculations suggest the energy output of even a microscopic white hole could exceed all the nuclear reactors on Earth combined. Futurists dream of tapping this via ergospheric mining, using magnetic fields to siphon energy from the particle jets erupting near a white hole's event horizon. The fuel, essentially recycled spacetime, converted into usable power with near-perfect efficiency. Of course, the engineering challenges border on fantasy. Containing something that repels all matter would require materials and forces beyond our current grasp. Yet the same was once said of splitting the atom. The most tantalizing twist: white holes might not just be hypothetical. Gamma-ray bursts, the most energetic explosions in the universe, sometimes defy conventional explanations with patterns that resemble theoretical white hole emissions. In 2022, astronomers observed a bizarre object nicknamed the Cow, which flared with the brightness of 100 supernovae before vanishing without a trace. Some theorists argue it matched predictions for a white hole's brief, brilliant lifespan. Others propose that dark matter's gravitational effects could be signatures of ancient white holes lingering from the early universe, their event horizons now stretched thin across cosmic time. Whether cosmic mirage or revolutionary reality, white holes force us to rethink the universe's architecture. If they exist, the cosmos isn't just expanding, it's breathing, inhaling through black holes and exhaling through white ones in an eternal cycle of destruction and rebirth. Every star, planet, or person might one day pass through this cosmic grinder, only to re-emerge transformed in another corner of space-time. Until we find proof, white holes remain the ultimate thought experiment, a reminder that even the most outlandish ideas can reshape science if we dare to follow the math where it leads. Forget the moon of dusty footprints and barren plains. The lunar poles are hiding a treasure far more precious than gold. Locked in permanently shadowed craters where temperatures plunge to -400 degrees Fahrenheit, lie vast deposits of water ice preserved for possibly billions of years. This isn't just frost. India's Chandrayaan-1 mission and NASA, a lunar reconnaissance orbiter, have mapped billions of tons of the stuff, enough to fill thousands of Olympic swimming pools. These icy caches transform the moon from a scenic overlook into the solar system's ultimate rest stop, a pit crew poised to fuel humanity's leap into deep space. The magic of lunar water lies in what it breaks down into: hydrogen and oxygen, the very components of rocket fuel. Transporting propellant from Earth costs roughly $20,000 per pound, a deal breaker for ambitious missions to Mars or beyond. But with on-site water mining, the moon becomes a gas station orbiting just 3 days away. Picture this: robotic harvesters boring into crater floors, extracting ice that's purified, split into elements, then chilled into liquid hydrogen and oxygen tanks. Future explorers could refuel landers for return trips or top off deep space vessels headed to the asteroid belt. NASA Artemis program is already prototyping this with Prime 1, a drill set to land near the South Pole in 2024, testing extraction methods in the moon's brutal cold. But water's value doesn't stop at propulsion. Every kilogram of lunar ice spared for life support saves another kilogram that doesn't need launching from Earth. Water shields against radiation when packed into habitat walls, grows crops in hydroponic farms, and when electrolyzed provides breathable oxygen. Private ventures like SpaceX and Blue Origin eye these deposits as economic cornerstones. A single ice-rich crater could supply a lunar settlement for decades. There's even speculation about exporting hydrogen to Earth's burgeoning fusion reactors, should the technology mature. The real intrigue, though, is scientific. Lunar ice isn't just practical, it's a time capsule. Comet impacts over eons delivered water laced with organic compounds, and the moon's lack of atmosphere preserved them perfectly. Studying its isotopic ratios could reveal whether Earth's oceans share heritage with these celestial deliveries. Some craters, like Shackleton, may harbor ice older than the solar system itself, offering clues to the molecular precursors of life. Challenges remain, of course. Mining in perpetual darkness requires nuclear or solar-powered rigs, and transporting ice to sunlit processing plants demands innovative robotics. Then there's the legal gray area. Space treaties forbid territorial claims but say nothing about resource extraction. Yet the stakes make these hurdles worth tackling. With lunar water, the moon stops being a destination and becomes a springboard, the first link in a supply chain stretching across the cosmos. Every glass of water drunk there carries an irony. This lifeless rock might be what finally lets humanity live among the stars. Somewhere in the direction of the constellation Bootes lies a nothingness so vast it defies comprehension, a cosmic void stretching nearly 330 million light-years across where galaxies should be but aren't. Discovered in the 1980s, this barren expanse, officially dubbed the Boötes Void, isn't just empty. It's aggressively empty. While typical voids between galaxy clusters might span a few tens of millions of light-years, this one is so unusually vacant that astronomers initially dismissed their own data, convinced their instruments had failed. Rechecking the numbers only deepened the mystery. The void's sheer scale shouldn't exist under standard cosmological models unless our understanding of the universe is missing something fundamental. What makes the Boötes void so unsettling isn't just its size, but its defiance of cosmic precedent. The Big Bang's afterglow shows matter was distributed nearly uniformly in the early universe, like sprinkles in batter. Gravity should have pulled that matter into a web of clusters and filaments, not left a gaping hole the equivalent of 1,000 Milky Ways lined up end to end. Some theorists speculate the void might be evidence of an ancient collision between our universe and another bubble universe in the multiverse, leaving behind a scar in space-time. Others propose exotic physics, like a concentrated blob of dark energy repelling matter outward, or quantum fluctuations frozen into the cosmos during inflation. Then there's the eerie possibility that we're simply looking at the wrong angle. What if the void isn't spherical, but a tunnel-shaped filament seen edge-on, making it appear emptier than it is? Yet the most startling revelation comes from the handful of galaxies that do cling to life inside the void. These isolated survivors, like the dim red dwarf galaxy MCG plus 0102-015, are the cosmic equivalent of desert nomads. Their stars burn oddly, their gas reservoirs are depleted, and their shapes are often distorted, as if the void itself is slowly starving them. Studying these loners could rewrite the rules of galactic evolution, showing how environment shapes destiny. If galaxies can persist here against all odds, might life? A planet orbiting one of these stranded stars would have a night sky almost devoid of neighbors, its heavens a black canvas punctuated by faint, distant smudges. The concept of alien takes on new meaning when your entire civilization floats in a sea of nothingness. Practical implications lurk beneath the philosophical ones. If voids like Boötes contain hidden forces or matter distributions, mapping them could refine dark energy models, helping predict the universe's ultimate fate. Their extreme environments also serve as natural labs for testing relativity. Light crossing the void experiences subtly different gravitational effects than in crowded space, potentially revealing cracks in Einstein's framework. Some cosmologists even speculate that advanced civilizations might eventually harness voids as cosmic shortcuts, using their low-density regions to minimize drag for near light-speed travel. But the void's greatest gift might be humility. In a cosmos obsessed with shining stars and swirling galaxies, the Boötes void whispers a counterpoint: absence has shape. Emptiness has weight, and in that nothingness we're forced to confront how much we still don't see or understand about the dark scaffolding holding up the lights of the universe. Every unanswered question about this void isn't just a gap in our knowledge. It's an invitation to look deeper, think stranger, and redefine what we call normal in a universe that clearly has other ideas. When light from a distant galaxy passes through the twisting fabric of spacetime, it doesn't just bend, it tells a story. Gravitational lensing, the phenomenon where massive objects warp the light traveling around them, has long been one of astronomy's most powerful tools. But recent anomalies in these cosmic funhouse mirrors are revealing secrets Einstein never imagined, from invisible worlds to the ghostly echoes of parallel realities. Take the case of El Gordo, a galaxy cluster so massive it bends light like a carnival mirror, creating multiple stretched images of the galaxies behind it. Normally, these distortions follow predictable patterns, but in 2014, Hubble spotted something bizarre. Certain lensed galaxies appeared brighter than they should have, as if extra mass lurked somewhere unseen. The culprit, an entire swarm of rogue planets, perhaps trillions of them floating freely between stars, their combined gravity subtly warping the light. These nomad worlds, ejected from their birth systems long ago, had been invisible until their collective weight betrayed them. Suddenly, lensing wasn't just mapping galaxies, it was exposing a hidden population of worlds outnumbering stars in our galaxy 2,000 to 1. Even stranger are the lensing events that defy explanation altogether. Some distant quasars flicker in ways that suggest their light is being bent not by a single massive object, but by something far more exotic, a cosmic string, perhaps a hypothetical defect in space-time left over from the Big Bang. Others exhibit weird, symmetric distortions that a few daring theorists argue could be signatures of mirror matter particles from a parallel universe tugging on ours through gravity. Though controversial, the math holds up. If another universe exists in higher dimensions, separated from ours by a membrane thinner than an atom, its gravity could still leak through, subtly altering how light bends in our own. The real magic happens when lensing unveils the unseen closer to home. Astronomers now use microlensing to spot exoplanets too distant or dim for traditional detection. As a rogue star drifts in front of a background one, its gravity magnifies the distant light like a lens. Any planets orbiting that foreground star create tiny, telltale spikes in brightness, a technique that's already revealed frozen worlds floating beyond Pluto's orbit and even potential, free-floating Earths untethered to any sun. The upcoming Nancy Grace Roman Space Telescope will take this hunt galactic, scanning for microlensing events across the Milky Way's bulge, where thousands of wandering planets might lurk. Yet the most profound revelations come from lensing's failures. Certain galaxy clusters bend light too much, their visible mass can't account for the distortion. This overlensing might be the best evidence yet for dark matter's existence, proving its gravity shapes the cosmos even as it eludes our detectors. Other anomalies hint at chinks in relativity itself. Subtle discrepancies in how light bends around massive objects could point toward new physics, like variable gravity or extra dimensions. Gravitational lensing has become more than a cosmic magnifying glass. It's a decoder ring for the universe's deepest mysteries. Every warped image, every unexplained flicker, is a clue written in bent starlight, waiting for us to read between the curves. Whether exposing hidden worlds or whispering of realities beyond our own, these distortions remind us that even light doesn't travel straight in a universe this strange. Deep within the crushing atmospheres of Neptune and Uranus, a storm of unimaginable extravagance brews not water, not sulfur, but diamonds. These ice giants, often overlooked in favor of their flashier gas siblings, harbor conditions so extreme they turn humble methane into glittering crystals, forging what might be the most opulent precipitation in the known universe. Here's how nature's alchemy works. The atmospheres of these planets are rich in methane, simple molecules of carbon and hydrogen. At around 5,000 miles beneath the cloud tops, pressures soar to over 1 million times Earth's surface pressure, paired with temperatures nearing 7,000 degrees Fahrenheit. Under these brutal conditions, methane shatters. Hydrogen atoms are stripped away, leaving bare carbon atoms to be squeezed into crystalline lattices, raw diamonds. These gems don't gently form, they're hammered into existence, then plunged deeper into the planetary interior, creating a perpetual rain of precious stones. Some models suggest diamond hailstones on Uranus could grow as large as a car, their surfaces searing hot from the friction of descent, only to melt back into liquid carbon near the core. The implications for technology back on Earth are staggering. Lab experiments using high-powered lasers have recreated snippets of this process, producing nanodiamonds in nanoseconds. If scaled, we might synthesize flawless industrial diamonds without mining, ideal for everything from ultra-precise surgical tools to quantum computing components. Diamonds aren't just pretty, their thermal conductivity and hardness are unmatched. Imagine spacecraft hulls coated in diamond-based armor, shrugging off micrometeoroids, or batteries with diamond electrodes that charge in seconds and last decades. Some researchers even theorize about diamondoid structures, molecular-scale diamond frameworks, that could revolutionize nanotechnology, creating materials stronger than graphene and more durable than steel. Then there's the energy potential. Uranus and Neptune's diamond rain isn't just a geologic curiosity, it's a planetary power cycle. As diamonds sink, they generate heat through friction, potentially contributing to these planets' bizarre magnetic fields, which are tilted and offset from their cores. Harnessing a similar process in reactors could unlock new forms of energy storage, dense, stable carbon lattices holding vast amounts of energy for gradual release. Private ventures like Brilliant Energy already experiment with diamond-based nuclear batteries, where radioactive isotopes coat diamond substrates to produce long-lasting, low-maintenance power sources. Of course, interstellar diamond mining remains firmly in the realm of sci-fi for now. The pressures inside these ice giants dwarf anything we can engineer, and descending into their metallic hydrogen oceans is a feat beyond current robotics. But the mere possibility reshapes how we view our solar system's resources. Every diamond on Earth was forged in the guts of dying stars or colliding continents. Neptune and Uranus remind us that the universe's vaults hold riches we've barely begun to imagine. Who knows, the next generation of supermaterials might not come from a lab or a mine, but from decoding the hidden storms of our most distant planetary neighbors. Some stars don't just flicker, they vanish. Take KIC 8462852, better known as Tabby's star. This unassuming pinpoint in the constellation Cygnus behaves like nothing else in the cosmos. In 2015, astronomers analyzing Kepler telescope data noticed its light dropping by up to 22% at irregular intervals, as if something colossal were passing in front of it. Not a planet, not a dust cloud, something far stranger, something that shouldn't exist. The leading theory, a Dyson swarm, a vast constellation of energy-harvesting megastructures built by an advanced civilization, encircling their sun to capture every photon of its power. The concept isn't new. Physicist Freeman Dyson proposed in 1960 that any civilization approaching Kardashev Type 2 status capable of harnessing their star's total output would need to build such a structure. Picture millions of solar panels or mirrors orbiting in formation, absorbing starlight and beaming it back to their homeworld as usable energy. The scale is unfathomable. A single Dyson swarm could generate orders of magnitude more power than humanity has consumed in its entire history. Yet Tabby's star isn't alone. Others, like Epic 244493986, show similar erratic dimming, while Boyajian's star dims in bizarre, asymmetrical patterns that defy natural explanations. But here's where it gets complicated. Nature has its own tricks. Some stars dim because of immense planetary debris fields, like the remnants of a catastrophic collision. Others host bizarre magnetic activity or swarms of comets. Even interstellar dust clouds could mimic a partial Dyson structure's silhouette. The key lies in the infrared signature. A megastructure absorbing starlight would re-radiate waste heat at specific wavelengths. Observations so far are inconclusive, but projects like Breakthrough Listen are scanning these stars for artificial radio signals, just in case. The implications of a confirmed Dyson structure would be staggering. It wouldn't just prove we're not alone, it would redefine energy science. Imagine tapping into even a fraction of a star's output. A single Dyson ring could power interstellar travel, terraform planets, or sustain digital consciousness for millennia. Some researchers speculate that if such civilizations exist, their energy needs might explain dark matter's missing mass. What if dark matter is just the waste heat of a galaxy's worth of Dyson swarms, glowing faintly in wavelengths we've yet to detect? Yet the true revolution might be philosophical. A Dyson builder wouldn't just be advanced, they'd be operating on timescales we can barely fathom. Constructing such a megastructure would take centuries, if not millennia, implying societal stability beyond anything humans have achieved. Their very existence would suggest that civilizations can survive their own technological adolescence, a hopeful counterpoint to the Great Filter's grim possibilities. For now, Tabby's star remains an enigma, but whether its dimming stems from alien engineering or an undiscovered natural phenomenon, it's already done something remarkable. forced us to look at stars not just as balls of plasma, but as potential power plants or beacons of civilizations far older and wiser than our own. Every new anomaly we find brings us closer to answering whether we're the universe's only engineers or merely the newest apprentices in a galaxy teeming with master builders. What if our universe is just one page in an infinite cosmic library? The answer might be written in the oldest light we can see, the cosmic microwave background, or CMB, the afterglow of the Big Bang. This faint glow, visible in every direction, has been meticulously mapped by satellites like Planck and WMAP, revealing an astonishing pattern. Nestled within its subtle temperature variations are anomalies so bizarre they defy conventional explanations. Cold spots stretch across billions of light years where they shouldn't. Strange asymmetries skew the radiation's distribution as if the universe itself were lopsided. Most intriguing of all, a curious axis of evil, an alignment of fluctuations that point in a specific direction, as if something beyond our universe were tugging at its fabric. These irregularities aren't just cosmic static. Some theorists argue they're fingerprints of collisions with other universes. Picture bubbles in a pot of boiling water, each representing a separate universe with its own physics. If two bubbles grazed each other in the moments after the Big Bang, the energy released could have left scars in the CMB, imprints of a multiverse we're only now learning to decode. The cold spot, for instance, might be a bruise where our universe brushed against another, draining energy from that region of space. It's a radical idea, but the math holds up. Simulations show such collisions could produce exactly the kind of anomalies we're observing. The implications rewrite reality itself. If parallel universes exist, they might operate under entirely different laws, some with stronger gravity, others where time flows backward, or where dark energy never accelerated expansion. This isn't science fiction, it's a natural extension of inflationary theory, which suggests our universe is one of countless pocket universes spawned during a hyper-fast expansion of spacetime. Some could harbor mirror versions of Earth, nearly identical but with subtle differences. Others might be so alien matter never coalesced into stars. The real shock, these universes could be closer than we think, hovering in higher dimensions mere millimeters away, yet invisible because they occupy planes of reality we can't perceive. Practical applications sound like fantasy, but the math hints at possibilities. If we could detect gravitational echoes from neighboring universes, we might exploit their physics for energy or propulsion. Imagine borrowing a parallel universe's weak nuclear force to catalyze fusion reactions here, or tapping into a dimension where light moves faster to send information instantaneously. Even wilder, if consciousness arises from quantum processes, could our minds interface with versions of ourselves in other universes? Experiments like the holometer at Fermilab are already hunting for space-time pixelation that could betray the presence of adjacent realities. Skeptics counter that these anomalies could stem from instrumental errors or unknown cosmic phenomena. But every alternative explanation, exotic dark matter, primordial magnetic fields, falls short of accounting for all the CMB's quirks. The multiverse hypothesis, while untested, elegantly ties them together. Future telescopes like the Simons Observatory aim to scan the CMB with unprecedented precision, hunting for telltale circular patterns or polarization signatures that could confirm or crush the theory. Whether these anomalies reveal parallel worlds or new physics, one thing's certain: the cosmic microwave background isn't just a relic, it's a portal offering glimpses beyond the edges of our cosmic bubble. Every strange fluctuation whispers a question. If there are infinite universes, what unimaginable versions of reality lie just beyond our grasp? The answer could redefine not just cosmology, but what it means to exist at all. Beyond the known planets, in the dark reaches of our solar system, something massive is tugging at the fabric of space itself. an unseen force warping the orbits of distant worlds with its gravitational pull. Astronomers call it Planet 9, a hypothetical giant lurking 20 times farther from the Sun than Neptune, so distant that a single orbit could take up to 20,000 years. The evidence for its existence isn't just compelling, it's written in the strange behavior of frozen objects drifting in the Kuiper belt, that icy graveyard of cosmic debris beyond Pluto. Take Sedna, for instance. This dwarf planet follows an elongated, looping path around the Sun that defies normal gravitational patterns. Even more peculiar are the so-called extreme trans-Neptunian objects, like the aptly named Goblin, which cluster in tilted orbits all pointing in the same direction, as if herded by an invisible shepherd. Computer simulations show only one plausible explanation: a planet roughly 5 to 10 times Earth's mass, tracing a highly elliptical orbit through the outer solar system. Its gravity would act like a cosmic comb, aligning these distant bodies with mathematical precision. Without it, their clustered orbits have just a 0.007% chance of occurring naturally, a cosmic fluke so unlikely it's practically a smoking gun. Finding Planet 9 wouldn't just add another world to our solar system's roster, it could rewrite the rulebook on how planets form. Current models suggest our system's giants, like Jupiter and Saturn, grew by slurping gas from the primordial disk around the young Sun. But a super-Earth or mini-Neptune this far out, that shouldn't exist unless it's a rogue planet captured from another star during the Sun's infancy. Or perhaps it formed closer in, then got catapulted outward by gravitational chaos in the early solar system. Either scenario would force scientists to rethink planetary migration, the dynamic shuffling that shaped our cosmic neighborhood. The hunt is already reshaping astronomy. Telescopes like Subaru on Mauna Kea scan the skies for Planet 9's faint infrared glow, while algorithms sift through decades of data for overlooked clues. Some researchers are even turning to citizen science, crowdsourcing the search through projects like Backyard Worlds. The challenge, Planet 9's extreme distance, means it could be 20,000 times dimmer than Neptune, a ghostly whisper in the cosmic static. Yet the payoff would be historic. Beyond solving an orbital mystery, Planet 9 might explain other solar system oddities, like why the Sun's spin axis tilts 6 degrees off kilter. Its gravity could have nudged the entire solar system over billions of years. And if it's an exiled ice giant, its atmosphere might preserve chemicals unchanged since the dawn of the solar system, a frozen time capsule of our origins. The most thrilling possibility, Planet 9 might not be alone. Its discovery could hint at a hidden population of distant worlds, rewriting the final chapter of our solar system's story. Every strange orbit, every gravitational anomaly is a breadcrumb leading us deeper into the dark, toward a truth far stranger than we've dared to imagine. From liquid water buried beneath Mars to diamond rains on Neptune, from the cosmic whispers of fast radio bursts to the staggering possibility of multiverses written in the afterglow of the Big Bang, each of these 30 discoveries isn't just a headline. They're keys to unlocking a future we're only beginning to imagine. Think of what's at stake: medical breakthroughs inspired by extremophiles in Europa's oceans, clean energy modeled after the Sun's fusion, materials tougher than diamond forged in the hearts of dying stars. These aren't distant fantasies, they're the next chapter of human progress waiting to be written. Consider how far we've come in just the last decade. We've mapped the cosmic web, photographed a black hole's shadow, and found building blocks of life on asteroids. Yet the most thrilling realization isn't how much we've learned, it's how much lies just beyond our grasp. The universe isn't holding back, it's practically shouting clues, from the methane mysteries of Mars to the gravitational tugs of Planet 9. Every anomaly, every unexpected signal is an invitation to dig deeper. But discoveries don't happen in a vacuum. They're born from the collective curiosity of scientists staring at data until their eyes blur. engineers tweaking instruments in wind-battered observatories, and even amateur astronomers spotting irregularities in backyard telescopes. The next groundbreaking revelation might come from a graduate student analyzing telescope archives or a crowd-funded satellite spotting an atmospheric oddity. That's the beauty of space exploration. It belongs to everyone. So here's the challenge. Don't just watch this future unfold. Be part of it. Follow missions like the James Webb Space Telescope's deep field images or the Europa Clipper's hunt for alien oceans. Advocate for funding planetary science and education, and most importantly, stay relentlessly curious. Ask the wild questions. What if we harness dark matter? What if we decode a message hidden in fast radio bursts? What if the great filter isn't ahead of us but behind us, meaning we're the ones who'll finally break the cycle? The universe isn't finished surprising us. Whether you're a scientist, a student, or just someone who looks up at the night sky and wonders, remember, every world-changing discovery started as a spark of curiosity. Keep fueling that spark, because the next revelation that rewrites our textbooks, the next breakthrough that redefines life on Earth, might just begin with you. The cosmos is calling. Let's see what we find when we dare to answer.